Here's another example from momentum. Example number 3 on your handout that I gave you yesterday. This is a bit different. It says the momentum of an object is 200 kilograms meters per second. What does the momentum become if I double the mass of the object, but I reduce the velocity to 1/3 of what it was? So I'm asking you here, given a momentum, to find another momentum without any other variables. I'm changing the value of m, I'm changing the value of v, but I don't know what it was to begin with. Like, okay, I'm doubling m, but from what? Like if it was 10, all right, that's great, now it's 20. But what was it? We don't know. We don't know. To solve a problem like this, whether it's in the context of momentum, which is what we're doing right now, or the context of electric force that we do in our next unit, or magnetic force that we do in our next unit beyond that, doesn't matter. If we want to solve a problem where we're changing the value of variables without knowing what they were to begin with, we're going to use a technique that I call variable value changing. And that technique involves writing down an equation that would work to solve the problem if we knew what the variables were. In other words, if we're looking for momentum and we knew what mass was and velocity was, then we would write down the equation P is equal to m times v. Agree? If I gave you mass and I gave you velocity, that's what you'd write down to solve for momentum. But we don't know what mass and velocity are. Okay, well, that's okay. We'll deal with that. I want to add a little subscript to the P. It's an O. It stands for original or old. The original momentum, the old momentum. Before I make any changes to it, this is what it is. M times V. And we know what that original value is. We're told that right in the first sentence. It's 200 kilograms meters per second. So look at what I've done so far. All I've done so far is written down an equation that's given to me on my data sheet and written down a number that's given to me in the question. So in other words, I haven't really done much myself at all. I've just written down a couple of things that have already been told to me. The next step is where I have to do something. The next step, I'm going to write down Pn. What do you think the n stands for? If O stands for original, then N stands for new. This is my new momentum. This is what the momentum becomes. This is the one I'm looking for. Before we go any further, I got to make a little confession here. Yesterday I told you the equation for momentum is m times v. I lied. The equation for momentum is mass times velocity. M is simply the symbol we use usually to represent mass, and V is the symbol we use to represent velocity. The equation is technically mass times velocity. We just represent it by M times V. Does that make sense? We could have called M Q if we wanted to, and then the equation would be Q times V, and that would work just as well, right? It would be a little counterintuitive, but it would work for us. The equation is mass times velocity. The symbol is M times V. Well, we're going to change the symbol here. The equation is still mass times velocity, but the symbol for M, for mass, sorry, is now no longer going to be M. It's now going to be 2M. Right? I'm multiplying mass times velocity, but my mass is if it was M, now it's 2M. It's still mass, but the symbol is 2M instead of M. Well, we multiply that by velocity, but what's the new velocity? What's the symbol for my new velocity? Good, 1/3 V. So what I want to do now is tidy it up a little bit, multiply those numbers together and pull it out front. What's 2 times 1/3? You guys learned this in grade 8. I know you did, because my son is in grade 8 and he's just learned fractions in December, just before Christmas, multiplying fractions and adding fractions. Grade 8ers can do it. You guys can do it, right? What's 2 times 1/3, Rudia? Good. It's 2/3. And we'll pull that number out front. 2/3 m times v. Look at this though, guys. Look at this. Look at how neat this works out. M times v. Oh, look. We know the value of m times v. We know its value. We wrote it down in our first step. It's 200. So what we're going to do is sub in that value for m times v. It becomes 2/3 times 200, which gives me 133. So, like it's almost a miracle here, guys. Look, we just found a value of momentum without knowing what m and v were. I wouldn't go so far as to say it's a miracle. It's not quite that far, but it is kind of neat, eh? Like we didn't know what m was, we didn't know what v was, but yet we still found a value of the momentum simply by changing the mass by a factor of 2 and changing the velocity by a factor of 2/3. Write down the equation. And clearly, today, the only equation that it could be is m times v. Down the road, it could be something else as well. Write down the equation. If you know what it's equal to, write that down too, and then write down the new value is equal to whatever it is with your changes. Make your changes to it and see what it works out to be. Yep. Good question.
I just did 2 times 100 is 200.
Yep.
And then times the math by 2, so that dividing the velocity by about 30.
Yep.
So 4 times 33 equals 130.
Yep. Yeah, you could. Yeah, you absolutely could. The question was, could you plug in values for m and v? You can, as long as you're consistent. I would stick with values of, personally, I would stick with values of 1 if you're doing that, or 100, something nice and tidy like that. The danger to that is that you start throwing these extra numbers in there, and you can start, depending upon the context of the question, convincing yourself that the mass is 100, where it's not, right? Not necessarily, at least. So you may convince yourself that you have a variable that you don't really have. It works if you don't take it too far. But it can lead you astray if you start convincing yourself that you know what that variable is. That make sense? Okay. You know what? I've always said, though, in Physics 20 and in Physics 30, if you can think of a way to do something that's different than the way that I do it, as long as it's not a fluke, as long as it's legitimate, then more power to you. Okay, you can always do it that way if it works, and that does, as long as you're careful. That does. All right. We're going to give you an opportunity right now to work on some check and reflect questions from your textbook. This is chapter 9 in your textbook, page 453, number 1 and 2, 5 to 9, 11, and 13 to 16. You can always tell which chapter it is by the first number here, chapter 9. Okay, chapter 9, page 453, 1 to 2, 5 to 9, 11, and 13 to 16. Let's have a look at one more example, and then we'll shut it down for the day here. Example number 4 says a 1,000 kilogram car moves at 10 meters per second, and a 1,200 kilogram truck moves at 12 meters per second. What's the total momentum and the total kinetic energy in 2 different scenarios? The first scenario, the car is traveling one way, and the truck is traveling exactly opposite on one plane. In the second case, the car is traveling north and the truck is traveling to the west on a different plane in a different dimension. Let's first find the momentum of each vehicle and the kinetic energy of each vehicle, and then we'll worry about combining them. We'll worry about the whole north-south, the northwest, and so on after we find the magnitudes of the momentum and kinetic energy. So let's say here the momentum of the car. Let's actually say the absolute value of the momentum of the car, or in other words, the magnitude of the momentum. If you don't put those absolute value signs around that, we're not going to lose any sleep over that at all, okay? The reason I'm doing it is technically because I'm not dealing with direction yet. I'm just finding the magnitude. You forget the absolute value signs, whatever. Okay, that's a small thing. The momentum of the car is 1,000 kilograms times a velocity, or a magnitude of the velocity, a speed of 10 meters per second, gives me 10,000 kilograms meters per second. The momentum of the truck is 1,200 times 12, which is going to give me 24,000 kilograms meters per second. You with me so far? Good there? Let's get the kinetic energy of each of them. And then again, we'll worry about combining them in question A and B later on. The kinetic energy of the car what is that? 10 squared is 100, 100,000, 50,000. The kinetic energy of the car is 50,000. And the kinetic energy of the truck this one works out to be 86,400. And there is a mistake back here. This isn't 24,000. This is 14,400, right? Thank you. Okay, good, good. We have the magnitude of the momentum and the kinetic energy of both of them. Now, how are we going to combine them down here? The total momentum. The total momentum in question A. Yep. Yeah, or you're going to add a negative, which is the same thing as subtracting, right? I'm going to phrase it, though, as an adding question, because it's a total, and total kind of infers addition. But it's the same thing, yeah. We're going to say 10,000 plus negative 14,400, because 10,000 is north, 14,400 is south. We add those up, and we get negative 4,400. Or we round that to 2 digits, it would be negative 4.4 times 10 to the 3 kilograms meters per second. Now let's find the total kinetic energy. What are you going to do here? Yep. Add them both together. 10,000 plus 14,000. How come we didn't add the negative? Sorry, not 10,000 plus 14,000, but 50,000 plus 86,400? Which gives me 136,400. How come I didn't add a negative there? Or subtract, as Cody said. Again? Because it's a scalar, because kinetic energy is a scalar and momentum is a vector. You have to pay attention to direction for momentum. You can't pay attention to direction for kinetic energy. Well, question B is a gooder, though. Love this one. Well, I like this question. I like this question a lot. Maybe I'm biased because I made it, but I think it's a good question. What if the car is traveling north and the truck is traveling west? What now? Let's deal with momentum. How do you add these two together? How do you find the total momentum when one is going north and one is going west? Is it the same? Do we just say 4.4 times 10 to the 3? We're adding, but we're using the addition rules for vectors, for two-dimensional vectors. What we've got to do is say, look, our truck is traveling north, and it has a momentum of 10,000 to the north. No, sorry, the car is traveling north with a momentum of 10,000. And the truck was traveling to the west with a momentum of 14,400. What's the total momentum? Look. We do the Pythagorean Theorem, right? Because it's two dimensions. The direction matters. The direction matters. And if you got a north and a west, then this is how we deal with direction. If we got a north and a south, this is how we deal with it. We have a north and a west, this is how we deal with it. Now we're going to find the magnitude of that momentum by doing the Pythagorean theorem. And we're going to find the angle, and that's important, the angle here, because direction matters. Using the inverse tan of 14,400 over 10,000. Thank you. 17,531. We're going to round that to 1.8 times 10 to the 4 kilograms meters per second. Thank you. That's the magnitude of the momentum, and the direction is, make sure you're in degree mode on your calculator when you do this, 55 degrees. That would be 55 degrees west of north. Had you drawn the 14,000 first and then the 10,000, then you would have gotten an angle of 35 degrees, but that would have been north of west. This is west of north, that would have been north of west. Lightning fast answer before I stop for the day, before I stop talking. Lightning fast answer here. What's the total kinetic energy in question B? Same as A. Why did we not have to deal with the X and the Y, the Pythagorean theorem, or anything like that for kinetic energy? That is your hand up. Well, you can answer it anyways. Why do we not have to deal with those components? Good. Good. Kinetic energy is not a vector, it's a scalar. The direction isn't relevant. So all we do is add them the scalar way. Okay? With momentum, we have to add the vector way either this way or this way. With kinetic energy, it's always just this way because there is no variation on adding scalars together.